to everybody. Here, Cristiano of Pi School, the lead AI scientist, together with behind the scene there are Lucia, Joao, and Francesco that are managing this tech talk. We welcome here Gabriele, which is, by the way, part of. I will present it now, but he is part of AI for People. So it's friend of Aina and Marta that were here together with us last week in the previous tech talk, talking about what is AI for people, ethics in artificial intelligence, so on and so forth. And also Gabriele is part of this non-profit organization. Okay, a couple of information more about Gabriele. He's a PhD student at the University of Bologna in Italy, and he's focusing especially on continual learning, that will be the topic of today's tech talk, and also deep generative models. He's the head of AI at AI for People, okay? And in addition, he's one of the lead maintainers of Avalanche, which is the most used continual learning library and part of the PyTorch library and ecosystem. Today, we will talk about introduce to us continual learning, which is a branch of machine learning that addresses the problem of not having all the data at once during training. But you see, there are cases where the data are collected through time, and data may also contain some drifts. And during the training, maybe we want also to solve many chains over time. And so continual learning, it's taking care, or it's trying to taking care of everything. So go ahead, Gabriele, welcome. And,
thank you. Yeah, thank you very much, Cristiano, for the for the nice presentation. I will try to share my screen. Let me know if it works. Okay, so you should see the slides here.
Yep.
Maybe. Okay, perfect. So welcome everybody. I'm honored to be here to talk with you about continual learning. Just a quick presentation. Cristiano already presented me, so I will be very quick here. I'm Gabriele Graffieti, which is a pretty difficult name for the non-Italian, so just call me Gabri. I'm a PhD student at the University of Bologna in Italy. I'm mainly focused on continual learning and generative models, so machine learning in general, artificial intelligence, even more generally. I'm also the head of AI research at AI for People, which is a non-profit organization that was presented to you by Marta and Dinah a week ago, I think, the previous week. So I wouldn't go into details about AI for People, just to say we are a non-profit organization. We have a lot of different people with different backgrounds. So if you're interested in AI, if you're interested in a social aspect of AI, if you're interested in ethics of AI, or also in do project with AI for the social good, please join us. We are a non-profit, so we are free to you are free to enter and to join us anytime you want. So you are more than welcome if you want to join us. Maybe just to know us. I'm also as Cristiano said, the Avalanche lead maintainer, which is a continual learning library that we will see in the last part of the meeting. Avalanche is recently part of the PyTorch ecosystem, so we are officially recognized by PyTorch as a pretty good project. So we are really happy about this. And I'm also a member of Continual AI, which is another non-profit organization mainly focused on collecting and unite together all the researchers in continual learning. So very briefly, the today outline. So what I will talk to you about. So first of all, we will start with what is continual learning and why continual learning is useful. We'll start by addressing one of the main problems of machine learning. You already maybe have a lot of courses on machine learning. You are on a series of talks and courses about machine learning. So maybe you already know how machine learning works. Maybe you also already know that there are some problems in here. Today we'll try to address one of these problems with continual learning. After that, we explore some continual learning scenarios. This is a typo, so continual learning scenarios. We will see what they are. After that, I'll try to introduce to you some continual learning strategies, so how to deal with the problem, how to actually implement continual learning in machine learning models. There are dozens of different strategies. I think we mainly focus on 3 of them. But yeah, as I said, there are many different ways to do continual learning. So this is just an introduction. After that, we will see how continual learning can be used for a more sustainable AI. And in the last part of the talk, we will use Avalanche, which is this library. And there is some hands-on part. I will show you how to use this library to basically simplify your work if you want to work on continual learning. But yeah, don't wait anymore. So this is the classical machine learning pipeline that you may already know. So if you want to use machine learning, you basically collect some data, train data, of course, validation data for validating the hyperparameters, test data to test your model. So you basically collect some data. More data you collect, the best is, as you may know, we are in the age of big data. So bigger this data set is, the better is. So you have the data collected. You can use some machine learning techniques, whenever machine learning techniques you want, whenever model you want. You train your model on this data, and after that you'll obtain this your beautiful trained model that can solve the task that you wanted to solve at the beginning. Okay, this is the classical machine learning pipeline. But where is the problem? Okay, I deploy this model in the real world, so I don't use anymore the testing data that I've collected, but I use the real world data that actually comes from the real world and the real sensors and the real scenario that there are in the world. I fed the data to my model, and is this model still makes good predictions with real world data? Can you see any problem with this? You have some ideas, you have some I don't know, you want to discuss something, please, if you want to answer this question, so what's wrong with that, please write down in the chat or open up your microphone and let's discuss it. So maybe I'll open the chat and see if anyone has write down something.
So there may be data drift. I mean, the distribution of data used for training may be different as the world evolves.
Yep. World change.
Yeah.
Things change.
Yeah. This is exactly what's wrong with this scenario. The world changes, data changes. You can have drift, or you can also want to update your model. So yeah, I have a model that does something. I want that the same model does something else. So what's wrong with this scenario? As you said, the real world changes. So data can change over time. So model can may quickly become obsolete and so on. And another important point is that trained data is only a small subset of real world data. No matter how big my data set is only a very small subset. Even the largest data set in the world is only a small subset of the real world data. This is particularly true in fields like robotics or self-driving cars where there are a lot of different situations that can occur, and I cannot have a data set that contains all the different situations that can happen when I drive a car, even the most remote ones. Another point is that this pipeline here, so collect data, train, and use the model, is not biologically plausible. So animals, humans do not learn in this way. We learn continually. Every day we learn something new. Every day we learn to do something else. Every day we update our knowledge. So we don't have a phase when we only learn, and after that we only exploit the skill that we acquired. The learning is continuous for our entire life. And the last most important point in this pipeline, when I train the model, I cannot adapt the model to anything new. For example, if I have a model that classical model that classify dog versus cat, if I want to classify dog versus cat versus horses, I have to retrain all the model. I cannot use the old model, fed them with only horse images, and expect that the model it's good after that. So this is the main problem here. So what is continual learning in a nutshell? Well, it's basically a learning scenario when we do not have all the data at once, but we discover new data as time progresses. More specifically, if you are more statistic based, more specifically, the data that we discover may not be a good approximation for the total data distribution. As an example, we want to train a self-driving car. We collect images in the summer. Maybe we collect a lot of different images, but yeah, if we collect images only in the summer, it is not a good approximation of the total data distribution of driving a car, because, for example, we don't have images with fog, we don't have images with snow on the street, maybe we don't have images with rain, we don't have images with all the wet winter conditions that, of course, are not here in the summer. Having said that, we don't have all the data at once, so we discover new data as time progresses and so on. So which is the first solution that comes to mind? Well, I have a model which is really, really good with the test data. I collect new data from the real world. Yeah, just train the model on this new data, just adapt the model, fine-tune everything you want on this new data, and everything will go fine. We'll see that well, maybe not everything will go fine. Yeah, for example, here there is an example. I collect some data from a training set. It can be anything. Let's say maybe something that it changes. Maybe, I don't know. We want to classify tweets for hate speech. So I collect everything that every tweet in the last year, for example. I label them. I train my model. And now my model is able to classify these tweets in, so tweet without hate speech, and maybe tweet with hate speech. So maybe this is the classification boundary that my model finds out at the end of the training. Again, yeah, it's pretty good in this case. But as you may know, the communication, the way we communicate, the way we write tweets and so on changes over time. Maybe new slang is invented and so on. Society changes, so maybe something that now is considered acceptable in the future is not acceptable anymore, and so on. So the way we define hate speech can change over time. So maybe after a year, I collect some other tweets, and this is the result. So as you can see, the boundary that I found in my original training set is no longer valid here, because, yeah, as I said before, communication changes. Something that maybe a year before is acceptable now is not acceptable anymore, and so on and so on. So what I can do? Well, I have this data, just train the model. Okay, perfect. Now I can classify perfectly the new tweet as hate speech or not hate speech. Let's do another example. Maybe next year, I collect other data. In this case, the model is pretty good. It's not a perfect model, but better safe than sorry. I also train the model in this new data. Okay, this is the perfect classification boundary for this data. This is just a recap. So with the training set here, original training set, I train the model. This is the best classification that I can find. After a year, I collect some other data. This is the best classification boundary. After another year, I collect some other data. This is the best classification boundary that I found. Okay, what is the problem here? Well, that the model, after 2 years, it's totally forgot how to deal with the original training data. So this is my final classification boundary after 2 iterations. If I try to classify the training set data or the original data that I used at the start, yeah, it totally fails. It's maybe the worst model that I can have in this kind of data. And also, if I collect all the data of all my 3 years, so I memorize all the data, I put it together. Yeah, as you can see, the classification boundary is no longer valid, even if in the whole data set of all 3 years, because the optimal solution maybe it's this one and this solution. So this classification boundary, it's not it's not similar to any classification boundary, any optimal classification boundary that I had in any of the 3 different stages of training. So I'm nowhere near the optimal classification boundary for all the data. So this problem has a very, very, in my opinion, beautiful name, which is catastrophic forgetting. Yeah, and the word catastrophic, it's really appropriate here because the model not only forgets, as in this case, how to deal with the past data, but it catastrophically forgets so many times. So the model totally forgets how to deal with past data. It's also known as catastrophic inference and so on. And yeah, if you want, the definition is the tendency of an artificial neural network or any other machine learning model that it's trained using what I call greedy algorithms. So basically all the algorithms that are based on the gradient or are based on optimizing something based on the current data. This is why this happening. It's happening because if I train the model with only this data here, the model is forced to optimize, in this case, the classification boundary in the current data. Yeah, the past. I don't have anymore the past data. The model is why the model should not optimize at its best with the current data, the classification boundary, if the model don't have access to the past data. So this basically is a problem that occurs in I think any model, or maybe the vast majority of models used nowadays in machine learning. And yeah, if it's also related to the stability plasticity dilemma in the brain, so it also have a biological counterpart in our brain, because also our brain have to balance the forgetting versus learning new thing, which is the stability plasticity dilemma. So even our brain has evolved in a way to avoid catastrophic forgetting. So if you really want to deploy artificial intelligence that is really intelligent, we also want to overcome this problem here. So the best solution, the first best solution that maybe come to your mind, it's why I can have to train my model only on the current data. Just memorize all the past data, and every time train the model on all the past plus the present data. So this is my training set data. After sometimes I collect new data, I join the new data with the past data, and I train the model again, and so on and so forth. This method, of course, is the most effective, because basically it don't have forgetting, because I I have all the data that all the past and current data anytime. But of course, there are some problems with this approach. So, well, of course, we need memory to store all the past data. And in many different scenarios, this is a problem. Let's, for example, let's think about self-driving cars. So basically, every time I do a trip with my car, I have to retrain my self-driving car model in my car with all the data from the last trip and all the data for all the past trips that I've done since I own my car. So yeah, it's really not memory efficient. But the most important problem with this approach is its time and computational power totally not efficient, because every time, for example, as an example of a self-driving car, every time we do a trip, we have to train the model with all the past data. So it may require a lot of time. It may require a lot of computation. So it's totally not doable for real time or for any model that I want to develop in the real world, basically. If there's a question?
Yes, actually,
okay.
More than a question, a comment.
Okay.
Because you're arguing that the cumulative approach is the best solution.
Yeah.
But what if some data, let's call it, since the world evolved, some data is no longer relevant, but actually can be detrimental to our model? So is there any concept of the data life cycle when some data point is no longer representing the situation that we are analyzing, and then we are actually better off removing it?
Okay, yeah, this is a very interesting question. And yeah, there is currently a line of research in continual learning, which is based on exactly the thing that you say. So not all the data is important. Maybe some data it's not important at all, because maybe it's only an outlier or something that it never happened. It happened only one time, and I'm sure that it won't happen in the future. But yeah, the real question is how I can know that some data is important or some data is not important. How I can be sure that some data will not occur in the future. So yeah, it's a research direction, but it's not so easy to do so. We keep things simple. This is an introduction. So in all our example, all the data is important. But yeah, this is a really good question, and of course, this is not always the case. I don't know if I answer your question.
Yes, I think it really depends by the type of data and by what you define by useful or not useful. The example you made for the self-driving car, let's say if tomorrow we change, let's say the way we drive from right-hand side to left-hand side, I mean, everything that the car has learned about how to turn, it should better be forgotten.
Yeah. This is actually a very good example. But yeah, basically because this is effective because you know that all the data is not effective.
Right. But it's like how do you determine it in other cases that may be not so clear cut?
Well, you can determine it by how can you determine? Well, basically, if you have some data that you can memorize some samples of all the different data that you experience. So, for example, self-driving cars. Every time I do a trip, I memorize some samples of data from every trip. And every time I do another trip, and every time I train the model, every time I acquire new data, I can compare all the past data with the new data. So basically, I can have some sort of difference between the past and the present data. And if some kind of past data, it's always very different to all the data that comes in the future. So it's different from the next. So some trips data is different from the next trip. Is also different from the next trip. Is different from all the trips in the future. I can decide to, okay, this data is not important anymore, or maybe it's one on a time data. I can drop it, but this is a very naive approach. Maybe there are some more optimized way to do so, but yeah, basically you compare data, and if the data if some chunk of data is always really different from all the future data that you collect in the future, maybe it's not worth to use it anymore.
Okay, thanks.
Okay. Okay. As I said before, the cumulative approach, so maintaining all the data, is the best approach, but it's not used because, yeah, it needs a lot of memory and especially a lot of time and a lot of computation. So we don't want to use the cumulative approach in continual learning. It's just a sort of upper bound. So every continual learning algorithm has an upper bound, which is the cumulative approach. You can do better in the cumulative approach because in the cumulative approach you have all the data at once. So it's basically a classical machine learning scenario. It's not continual anymore because you have all the data every time. This is some different scenarios that can occur during continual learning. So basically, we divide our stream of data in different experiences. And we all only have access to the data of the current experiences. So this is the past experiences, so the past trips remaining in the self-driving car examples. So the data of the past trips is not accessible anymore. I cannot memorize this data here. I only have access to the current data, and of course, I don't have access to the possible future data. This is my model, in this case a neural network, but I can really have any model I want here. In base of the type of data that I have here, the scenarios can be divided into three different scenarios. So the first one is new instances. In this case, all the classes are present since the first experience. I'm talking about classification scenarios here. So we are talking about classification because it's the most common, it's the most studied, and the simpler task to solve here. But of course, continual learning can be used in many other different tasks. So, for example, detection or many different machine learning tasks. But we stick to classification because is the simple here. So we can have new instances, as I said, where all the classes are present from the first experiences. So in the subsequent experiences, so the present and the future, I only see new examples or different examples of the same classes. Returning to the self-driving car example, maybe this is the model that is used to classify what kinds of vehicle are around me. So there is a car, or there is a bike, or there is a pedestrian, and so on. I already know the classes from the start, and of course, at every trip, I see different examples or different examples of the same class. I see different cars, different pedestrians, different people, different bicycles, and so on. Another approach can be the new classes approach or the NC approach, in which each new experience contain data from different classes than the previous experiences. This is maybe the most difficult scenario. So basically, in any experience, I see objects of different classes that I've never seen in the past, and the object that I see in this experience won't be seen in the future. So as an example here can be maybe a I don't know, a domestic robot that interact with some objects, but every time this robot interacts with different objects. So maybe from one interaction interacts with balls, the next interaction interacts with bottles, the next interaction interacts with, I don't know, smartphones, and so on. So basically here I want to update the knowledge of my model in order to interact with different objects every time, but not forgetting how to interact with the past object, basically. Last but not the least is the NIC, which is the union of the new instances and new classes approach, which is called new instances and classes, and in which in each experiences each experience can be composed of new classes, so new objects that I never seen in the past, or even different examples of objects that I already know. So same example of the domestic robot, maybe first experience I interact with some bottles, second experience I interact with balls, third experience I interact with bottles, but not the same bottles of the first experience. This is the three main scenarios for continual learning. Okay, so why we want to use continual learning? As I said before, we want to update my model with new data, and this is different from fine-tuning because with fine-tuning you basically have a pre-trained model, and you want to fine-tune the model with new data, but you are not you are not interested in the performance of the model with the past data. So as an example, I train a model in a very, very large data set in order to train the feature extractor and so on. I fine-tune it to my data, but I'm no longer interested in the performance of the model after the fine-tuning on the original data used to originally train the model. I'm only interested in my data, in the performance on my data. On the other hand, here in continual learning, are interested in the performance of the model with all the data. So even the past data for us is interesting. We don't want to lose or to catastrophically forget the knowledge that we already acquired. Another reason that why we want continual learning is that maybe we don't want, or it's not possible to store the whole data. So we only have access to the current data and we cannot store anything. This is especially true for all the scenarios when we deal with privacy or secure data. So for example, biometric data usually cannot memorize biometric data, or for privacy reason, we cannot memorize the faces of people that we collect, for example, from security cameras at the airport, and so on and so forth. Another reason is that we want to update the model as soon as new data arrives. So we do not want to wait to collect some large amount of data and then train the model. We want to have the latest and the best updated model as possible. So as soon as new data arrives, we want to train the model, and a lot of different scenario when continual learning is actually required. For example, also as I said before, when we have a model that can do something, so for example, can classify some kind of classes, we want to extend the knowledge of this model to classify also some other kind of object, but we do not want to lose the performance and the knowledge of with the old data. We want to expand and adapt the model and increase its knowledge, not to just to fine-tune it and so on. Okay, so there are different ways to reach this continual learning, to reach and to deploy continual learning. There are, even in this case, three main different ways to do it. So the first one is the architectural strategy. So basically, In case, for example, of neural network, the model is expanded, new parameters are added, new layers are added in order to make space for the new knowledge that I want to learn. Yeah, this works pretty good, but does not scale well, because if I want to learn a lot of different new experiences, I want to insert in my model a lot of new knowledge. Of course, adding parameters does not scale well, because I can end up with a very, very, very huge model that it's difficult to train and so on. And of course, it's not biologically plausible, because our brain does not grow every time we learn new things. So yeah, it grows when we grow, but for example, it doesn't double its number of cells, number of neurons, and number of connections every time we want to learn a new skill or a new ability. Another method to enforce continual learning is by regularization. So, for example, adding term to the losses, force the model to not change some way that are important. We will see a strategy that to that. Basically, these regularization methods are mathematically sound. The mathematics is really beautiful. In theory, they work perfectly. But in practice, they are very, very difficult to optimize. They are difficult to implement. And if you have high-dimensional data, such as images, sound, videos, and if you have a lot of experiences, so a very, very large stream of experiences in order of 100 or 1,000 of experiences, in general, the regularization method does not scale very well. Last but not the least is the rehearsal or replay approach. When you, as I said before, you memorize a small part of the data for each past experience. So you don't memorize you don't memorize everything, but you memorize just some examples. This is really, really straightforward. It works pretty well. In many cases, is the only strategy that works. But there are three main and very and very bad, I would say, cons. So you need memory. And memory is cheap, but it's not infinite. And if you have a lot of experiences, for each experience you want to memorize something, you end up using a lot of memory. So you need memory. You cannot use replay in all the privacy or when you have to deal with data that you can't basically memorize. And of course, computation, because every time you want to learn the model, you don't you want to train the model, you don't train the model only on the current data, but also on all the replay data, which is, of course, is less than if I memorize all the past data. So it's only a subset, but it's new data, and every time I want to optimize the model, this data sum up to the current data. It requires more computation, requires more times, and so on. So I'll present to you this strategy, which is called AR1, which is in the intersection between architectural and regularization. So basically, I can explain to you two different strategies at the cost of one. So we see how can architectural strategy works and how regularization strategy works, just explaining one strategy. So it's pretty cool. Okay, let's start with the architectural part, which is Civware, it's called. So the problem here, it's basically in the last layer of the network. As you may know, all the first layer of a neural network are basically to extract features, and to extract feature. And the last layer or the last few layers of the network are used to actually classify the data points. So of course, the main problem is in the last part of the network, so in the classifier. This is a problem, for example, in case of the NC or the NIC scenario that we we see before. So when you don't have all the classes in any experience. So for example, in this case, in this particular experience here, I only have these 3 classes. So only these 3 classes are present. In this case, what happens to the network? Well, all the weight associated to these output neurons are optimized because I have the data that correspond to these classes. So I optimize all the weights corresponding to these neurons. But all the other neurons, I don't have any data. I don't have any data that correspond to these classes. So basically, when I train my model, the output of this neuron it should be always 0. They are not 1. They are always pushed toward, you have to output 0 all the time. So it happened that the weights associated to these neurons are pushed towards very, very low value. So in this case, I change my experience. In the experience before, these 3 classes are present. In this experience, these 3 classes are present. Same way, I trained this weight before, but now I don't have any example for these classes. So the weight associated to this neuron are pushed to output 0. So basically, I totally forgot the weights and the knowledge that I learned before. So there is a catastrophic forgetting in the very sense of the word here. How can I solve it? I can make a copy of the output weights. Here is the matrix of the weight. So every element in this matrix is a weight. So for example, in the first experience, I have only the first 2 classes, and I learned the 2 classes, which are here denoted by this color here. And as I said before, the weights of the classes that are not present, so I don't see any example of these classes, are pushed toward very, very low value, because basically the output neuron have to output 0 every time. So next experience, I have these 2 classes here. So what I can do, I can memorize. So I can freeze and memorize and take apart this weight, because these are the weight these are the good weights of the last experience. So I don't want to lose this knowledge. I can make a copy of the weight matrix here, initialized to 0. And now I can learn the weight of the new experience. So basically, I learned the weight of these 3 classes, and for the first and the 5th class, all the weights are pushed to very, very low value, because basically I don't have any example, so I always want to output 0 for this neuron. After that, here denoted in the pseudocode, I do a consolidation phase. So I have the old weight that contain the old knowledge about the old data. I have the new weights that contain the knowledge about new data. I basically put them together, not of course putting them as is, but following using some weight and basically consolidate together. This is the algorithm. I don't want to go into details, because just to give you an idea. And after that, the weight of my last layer are this one. So all these weight are trained and correctly output the correct class. So this is the weight of the classifier. The weight of the classifier are correctly trained for both the 2 experiences. And so this becomes my new old weight for the next experience. I basically have another weight matrix initialized to 0. I retrain, I reconsolidate, reconsolidate, and so on and so forth. And this basically solved the problem for the last layer of my neural network. For all the other weights of the network, so all the weights of the feature extractor, the AR1 algorithm uses another continual learning strategy, which is called EWC. which is first developed by guys at DeepMind. How IVC work? Well, it's the idea is quite simple, but the implementation is not so simple. So I'll try to give you the idea. As you may know, neural networks are over-parameterized. What it means that you have many more parameters than training data. Basically, neural network nowadays, you have millions, tens of millions of parameters. And basically, when you have millions of training data points, you have a very, very big data set. So basically, your model has more parameters than training data. This means that many configuration of parameters can lead to the same performance. So if you have a different configuration of parameters, so your network is configured in two different ways, these two different configuration can lead to the same performance. If the idea it's of EWC, it's maybe condensed in this figure better. So if, for example, this is in the parameter space, all the possible parameters configuration of your network that leads to good performance to your first experience. And these all are all the parameter configuration for your network that leads to good performance on another experience. If you basically use the fine-tuning or naive approach, you go to here, for example, to here. So you are not you are good for the task B, but not good anymore for the task A, because you switch from here to here. You basically add a penalty to the loss. You'll soon see how, in order to not go to here from here, but go from here to this part here, which is a subset in the parameter space when the parameters are both good good for the task A, so for the first experience, for example, and from the second experience, in this case, it's called task B. So you basically try to change the behavior of the training in order to not optimize only with the current data, but try to stay in the optimality region also for the past data, obviously without having access to the past data. So how can we do this? We can add a penalty to the loss for each parameter, which penalize the model if the parameter is moved. So basically, if I try to move a parameter, this term penalize me. So I'm in a situation where moving the parameter is penalizing. So basically, I'm forced to not train the model, basically, to not move the parameters. But of course, not the parameters are equal. As I said before, we are in the network are over-parameterized. So there isn't only one configuration of parameters that lead to good results, but there is a subspace of different configuration of parameters that leads to the same good results. So we want to penalize more if I move the parameters that are more important from the past task, and I don't want to penalize, or I want to penalize less the parameter which is not important. So I want only to move the knobs that do not penalize the performance on the old task. Okay, how can I do this? So how can I estimate the importance of every weight in the network? Well, this is some kind of statistics or some kind of theory involved, but very basically, suppose that after I train my model on one experience, all the parameters are optimal for the data in the current experience, obviously. So I'm in the maximum likelihood situation. So if I am in this situation, a slight change in every parameter decrease this likelihood, because every parameter is optimal in this case. But if changing a parameter does not change the likelihood much, so yeah, there is a decrease in the likelihood, but not so much, well, okay, this parameter is not important. and can be changed more freely. So the weight associated to the changes in this parameter are smaller than the weight maybe associated to parameter that if I change, the likelihood basically drops to 0. How can I quantify this information? This is this statistical object, which is called the Fisher information matrix, which is basically do this. I don't want to go into details. If you are curious, please ask me about more. But my objective here is not to go into all the mathematical details, just to give you an idea. And yeah, basically the idea is I have a matrix for which contains a weight for every parameter, and if I change the network, I also want to add to the loss a term that it's weighted by this matrix times how much I would like to change this parameter. So basically, main idea, I'm forced to only change the parameter that doesn't matter much for the past data in order to learn new knowledge and to train the network. So basically, I blocked all the parameters that are important for the past knowledge. So if a parameter contains a lot of it's very, very important for the past knowledge, I don't want to touch it. If a parameter is not important, so I can freely change it and the performance doesn't change don't change so much, okay, I can use this parameter in order to acquire new knowledge. I don't know if it's totally clear. Yeah, it's not so easy, but this is how it works, these methods here. So using AR1, so which is the combination of CWR and EWC, there are some plots of some performances. So this is some other continual learning algorithms. This is naive here. So as you may see, just fine-tuning the model, of course, the performance is very, very poor. This line here is the cumulative approach. So I memorize all the data, and I always and every time I train the model with all the current and past data. So it's the upper bound. As you can see, with different neural networks, so with 9 in this case incremental experiences. Here AR1, which is this line here, which is the higher line, outscore all the other continual learning strategies. This is other test that we did with many more incremental experiences. So 79 here, I guess, 191 here, and 391 here. And yeah, as you can see, some method works pretty well when the number of experiences is not too high. But yeah, basically every continual learning method apart from EWC here and this other method here basically drops its performance at the number of incremental experience. So the number of times that I train, I would like to train the model increases. So basically only few algorithms, and AR1 is one of them, can deal with a very, very large number of incremental updates and incremental experiences with new data and so on. The last, but not the least, technique that I want to show you, is the replay. So basically, as I said before, storing part of the past experiences data and use it when the model is trained on the new data. Of course, if I memorize all the data, the replay approach converges to the cumulative approach. So if I have all the data, is the upper bound, and I can do any better than this. But the interesting part here is that only a small portion of the data is more than sufficient to effectively contrast forgetting. So just memorizing few samples of the past data is effective to contrast the forgetting. And as I said before, this is really the only approach that works with high dimensional data or a very, very huge number of incremental experiences. How it works? Well, I have an external memory here. Every time I memorize some data into this external memory from the past experiences, and I use this data here alongside the current experience data when I incremental train my model. The pros of this strategy are that the catastrophic forgetting is highly reduced. It's simple to implement, just store some data in some memory and use it alongside the current data. So it's very, very easy and straightforward. And another pro is that memory is cheap, abundant. So I can have access to terabyte of memory with easily. The cons is, memory is cheap, is abundant, but it's not infinite. While the stream of experiences can be infinite or can be very, very long. And if I don't have an infinite memory, so that I have a constrained memory, at some point I run out of memory and I have to basically start to drop some past knowledge that can be useful in the future, maybe. What about privacy, private data? As I said before, I not always can memorize the data. So if I have to deal with private or privacy-related data, I cannot use the replay approach. And also it's not biologically plausible because, it's true that in our brain we have memory, but our memory is not a perfect memory that remembers everything and perfectly. It's quite different. Our brain doesn't work as is. So it's not biologically plausible also. Okay. So this is the problem of the replay approach. So I have a limited memory. I cannot store private data and so on. So you have some ideas of can we solve this problem? So if you have any idea, please write in the chat or open your microphone. So basically, I want to use all the benefit of the replay approach, so replaying all data, but I don't want to memorize the data. So if you if you have any idea on how to solve this issue. Okay, maybe you don't.
I don't know. Maybe you can try to, let's say, store not the full data, but some kind of, let's say, essential features that preserve privacy and save space.
Yeah.
Some kind of, I wouldn't call some kind of synthesis of what is a data point, but then you need to define what is the level of synthesis which is still useful to you, but without saving the full data, the data point.
Yeah, you're in the right direction, because saving, for example, the features or the not the actual data, but some extracted feature, maybe it's not always the case, but you could preserve the privacy, but you can reduce the space required to store a data point. So, for example, instead of an HD image, you can store, I don't know, 1,000 values instead of maybe millions of value for an image. But the problem of memory remains. You only postpone the moment when you run out of memory. But you are in the right direction. So the answer is this one. So I don't need a memory. I have another machine learning model, which is a generative model that generates the past data. So no memory is needed. The memory is fixed to the dimension of this generative model. So I never run out of memory. It's more biologically plausible because even in our brain, we use some sort of generative mechanism to generate memories. And using a generative model, I can generate, I can basically generate every amount of data that I want and so on. But of course, there is another problem. So how I train this guy here. And this is also this is still a pretty unsolved problem. I'm trying to address it in my recent work, but yeah, it's still an unsolved problem how to train the generative model. But I just want to show us this to maybe let you know that you can overcome the memory limitation, and just to let you know that, yeah, this is the state of the continual learning research now. Okay, I'm almost finished. Maybe I'm running out of time. So just a note on sustainability. Why continual learning can increase the sustainability of AI application following the sustainable AI principle. Maybe Aine and Marta last week talked to you about these 4 sustainable AI principle, which are defined by, I think, the European Union. I'm not really sure. So every sustainable AI application must follow this principle. So how continual learning can help machine learning application can help artificial intelligence to in this way. So point by point, efficiency, and scalability. Well, efficiency is the main pro of continual learning, because I don't have to train my model on all the past and current data. I have to train my model on the current data. So it's more efficient and it's more scalable. Fairness, privacy, and security. As I said before, continual learning can work with privacy and secure data, because if I don't use the replay approach, I don't have to memorize anything. I don't have to have access to the past data. So I only work with the current data. So it's basically privacy free. It's privacy oriented, and can work with all this kind of data. It also can work with privacy data, because I can have a continual learning model directly on my device. So I don't need a central server. When I send the data, the server do the computation and give me the trained model, but I can use continual learning directly to mobile phone, directly to embedded device, because it's efficient. So basically, there is no data transfer. I can train directly my model in the same device that acquired the data without data transfer. So it's more privacy, it's more secure, and so on. Accuracy and robustness. Well, this is also another point that continual learning can help. It's more robust because it's basically it's developed for robustness and for accuracy. Basically, the world changes. I want systems that are always up to date with the new data, with the new trends. If the data changes, I want a machine learning model that can detect these changes and can always be accurate, even if the data changes, robust to data changes. So this is all characteristics that continual learning has natively. So even this point nailed. The last point, explainability, transparency, and accountability. Maybe it's the most difficult point here to address, because continual learning, it's not really transparent. We still use black box model like neural networks or other machine learning models that are not explainable and not transparent, and so on. But we can do something in that regard, because in continual learning we train our model continually. So if at some point we recognize that our model does not perform well anymore, or do something that is not wanted, we may ask, okay, what is the last point that my model doesn't have any problem? Okay, yesterday my model was perfect, no problem at all. Today there are some problems. Okay, I know exactly in what kind of data is used to train my model. So in this case, I can more easily found out some problem with the data, maybe, or found some why my model does not perform in an expected manner anymore, and so on. So continual learning in general can increase the sustainability of machine learning application. If you want to know more, there is this paper. I put here the link. It's open access, so you can read it. It's very, very easy to read, written by my fellow and colleagues, Andrea Cossu, Marta Ziosi from AI for People, and Vincenzo Lo Monaco. It's called Sustainable Artificial Intelligence Through Continual Learning, and it's basically a broader discussion of all the things that I just said to you about these 4 sustainability points. Okay, maybe I'm running out of time, so just to let you know, this library here, which is Avalanche, which is a continual learning library. Why a continual learning library? Well, because where we can start with continual learning, if I am interested, there are many libraries for machine learning, for training neural network, for example, PyTorch, TensorFlow, Keras, Scikit-learn, and so on and so forth. But if I want to use continual learning, where I can start? Well, you can use Avalanche, which is an open source continual learning library. It's based on PyTorch. It supports continual learning classification, detection. It also supports reinforcement learning, in this case, continual reinforcement learning, and many more different stuff. There is a native support to create the benchmarks. So I have a data set. I want to create a benchmark. So, for example, any benchmark or a new classes benchmark. Everything is managed by the library. I only need the data set, and I say to the library, please create this benchmark with this number of experiences, and the classes split it in this way, and the library do everything for yourself. There are many strategies already implemented. There is AR1, there is AWC, CWR, and a lot more. Many metrics are already implemented. There are visualization tools based on TensorBoard and 1DB. And as I said at the start of this talk, is part of the PyTorch ecosystem. So we are officially certified by PyTorch as a good project. So I'm very honored about that. Here's the link. If you want to use it, there is the documentation, of course, the epidoc. There are a lot of tutorials in the website. And using Avalanche is as easy as do simply pip install Avalanche lib, and you basically have all this functionality. I've prepared a demo, but maybe you are running out of time. So
sorry, Gabriele.
Yeah.
Just to okay. Thank you so very much. It was really interesting. And then I kindly ask you if you can send me the slides so I can share them with. So at this moment, some of the fellow have another call.
Okay.
So maybe need to quit the presentation. So do I, because I'm into the same call. So I need to run away. But if you are available and the other fellow are interested and they have time, I don't want to interrupt the call, and you can go on with the presentation. Unfortunately, I cannot be there because really I need to go with the other fellow to discuss and to present our work to the sponsor. So I'm so sorry, I will quit here.
No.
You can go on, and for the other fellow, you can stay here, and so thank you so much.
No, thank you, Cristiano, and sorry again.
No,
okay.
Don't worry.
Perfect. I stay here if anyone is interested. So
I will also stay here, but I'm muting myself. Okay.
Yeah. Okay, so yeah, if you have another course, please you can leave now, and I'm sorry for the delay of 10 minutes, I guess. If you want to stay here, I'll try to answer the question in the chat. And for the ones interested, I have a brief demo on Avalanche. So let me know if you're interested, if you want to.
Yeah, I mean, if you have a quick demo, it will be good, at least for me. And then I
Okay.
speak for many others.
Okay, perfect. So maybe I'll first do the demo with Avalanche, and after that I'll answer all the questions in the chat. That I see that there are a few of them. Okay, I share my screen again. Okay, perfect. Now you let me know if you see my screen.
Yeah.
Okay, perfect. Reconnect. Okay. So how to use Avalanche? As I said before, is as simple as installing using pip install Avalanche lib. So I prepared this Colab notebook just to show you all the basic functionalities and how you can create a benchmark and use the strategies and do the training. So first of all, let me check if we still have the GPU. Sorry. Okay. So let's first install Avalanche. Okay, it shouldn't require so long. I tried this demo before, but obviously now there will be something that that gone bad, as always when you do live demo. Okay. Now Avalanche is installed here, so we can clean here. Let's check if everything is installed. Okay, I don't know if you are familiar with PyTorch, or maybe you are more familiar with Keras or TensorBoard, but yeah, Avalanche is basically based on PyTorch, so I will use PyTorch. If you don't understand something, if you don't, if there is something that it doesn't click to you, please let me know. But yeah, this is a really basic and easy example, so it shouldn't be anything that it's too hard. Okay, so basically, let's see if you are on the GPU. Yes, perfect. Okay, so let's first create a model. In this demo here, I want to use the MNIST dataset, which is a dataset of handwritten digits. And I want to use the NC, so the new classes benchmark. So every experiences contains new classes that are not have not been seen in the past. I never seen the same classes in the future. I want to create 5 incremental experiences, each experience is containing new classes, of course, because I have 10 classes in total, so 2 classes for each experience. And I want to train a model that is able to classify all the different digits, but without seeing them all together, as I can do with a classical machine learning algorithm, but 2 at a time. So first, I want my model to see only the 0 and the 1. After that, I train the model with 0 and 1. After that, I want my model to see only the 2s and the 3s, but not the 0 and 1. 0 and 1 are not accessible anymore, and so on and so forth for all the digits. So, okay, well, let's first create a simple model. So it's just a multi-layer perceptron with a linear layer and an output layer. Very simple. Okay, let's here create the two dataset. I use the Torch Vision call. So basically, Torch Vision, which is a PyTorch extension. Okay, of course, something doesn't work. Okay. and these basically create create and download for you the MNIST data sets. Of course, it doesn't work. Okay. If you don't have the dataset, it downloads the dataset for you. Here I create the train dataset, all the training data, training uguale true, and the test dataset giving training uguale false. This is basic PyTorch. So Avalanche, it's not here still. So okay, this is the first Avalanche call. So I have the two datasets. I have the train dataset and the test dataset. I want to create the benchmark, as I said before. So 5 different experiences. Each experiences contain new classes. So I create an NC benchmark, which I import here from Avalanche benchmarks generators. Import NC benchmark. This create or generate a new classes benchmark. As train dataset, I give to this function the train dataset that I downloaded before. As test dataset, I give the test dataset that I downloaded before. I want to use 5 experiences. Of course, here the number of experiences have to be a divisor of the number of classes. In this case, I have 10 classes for MNIST because 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 1 class for each digit. I cannot have 4 experiences here because in the NC benchmark, the number of classes in Avalanche have to be the same for each experience. If I want to have an NC benchmark with a different number of classes for each experience, I could do it obviously, but using using a different method, which is not the NC benchmark. So here I can use only one experience. So basically machine learning. So all the data at once. I can use 2, I can use 5, and I can use 10. Okay. In this case, I use 5. So there are 2 classes for each experience. Task label equal false. Task label in continual learning, I can also return the number of the experience. But in this case, I don't want to return it. It's some kind of simplification, but yeah, don't worry about this. It doesn't matter now. I can define here the class order. If I'm not defining the class order, the class order is random. So maybe in the first experience I can have, I don't know, the 5s and the the 9s. In the second, okay, and the 7 and the 0s and so on. But here I can define the order. So I want this order of the classes here. So I want the 0s and the 1, then the 2, then the 3, then the 4, and so on and so forth. And yeah, just as other PyTorch method, I can define the transformation. I just want to convert the images to the tensor. So it's a basic transformation to tensor and so on. And here the benchmark is created. So now I have this benchmark object, which is basically, it contains my training experiences already divided and already ordered. For some well-known and famous benchmark, as this benchmark here, which is called the split MNIST benchmark. So each experiences have different classes of the MNIST dataset. In Avalanche, there are already defined the call without the need to create the dataset, download them, and create the benchmark. But just there is an error here. But I can just call this method here, basically without creating the dataset, without creating the benchmark. So I can create the benchmark just with 1 line of code, basically. So I want to create a split MNIST benchmark with 5 experiences. That's all. But yeah, I use this longer version just to show you that you can have any dataset you want, your own dataset, your own data, and you can basically create a benchmark with your own data. you don't need to have a well-known dataset like MNIST or ImageNet. Maybe you can use your dataset or any dataset you want here. Okay, just create the optimizer for the model, the loss. Okay, nothing interesting here. Okay, another interesting part in Avalanche is the evaluation plugin. As I said before, there are a lot of different metrics, a lot of different visualizations that are already present in Avalanche. So, for example, here I want to log the accuracy at the level of experience. So after each experience, I want to log the accuracy, and at the level of stream. So I want to log the accuracy in the test set for each experience. So every time I train my model, I want to test it in each experience, even in the future data. So in all the test data, and log for each of the test experiences the accuracy, and I also want to log the overall accuracy on the test set. So I have all the test set, I want to log the overall accuracy. I also, for example, I want to log the confusion matrix here. And as loggers, I want to use the interactive logger, which is basically the console logger, and the TensorBoard logger here. So I also log all the plots and the confusion matrix on TensorBoard. Unfortunately, I tried a lot of time this evening, but I'm not able to show you TensorBoard here in Colab. But trust me, it works. And today we only see the console logger, but the TensorBoard logger, it works. It's just that I'm not able to show you the TensorBoard output here in Colab. Okay, so here we define the strategy. As I said before, there are a lot of different strategies to choose. For strategy naive, which is the fine-tuning strategy that I talked about before. So basically, it trains the model on the new data without any protection, without anything. So I have the new data, train the model. New data, train the model. Without any protection, without any continual learning optimization. So it's just the fine-tuning, the strategy here, just to see how the forgetting is catastrophic, even in a simple task like classifying the digits. Okay, I create the strategy, as I say, three lines already implemented. So here there is the training and the evaluation of the model. So for each training task, so for each training experience, I should have called it in my benchmark, I train the model, and after each experience, I want to evaluate the model using the test the test stream the test stream of my benchmark. So if I run this cell, hopefully we can see that it works. We should also see some. Okay, perfect. It works. I set here the number of epochs. So for each experience, I want my model to train for 2 epochs, 1 and 2 here. The train the train mini batch size, the evaluation mini batch size, and some other the device. So it's on GPU and some other property of my strategy. Okay, so let's see. This is the confusion matrix printed here in the console. It's not the best visualization possible, but it's okay. As you can see, I trained only the first 2 digits because in the first experience only the digits 0, 1 are available. As you can see, my model has learned pretty well to classify the 0 from the 1, but of course all the other digits are totally wrong because my model cannot see in the future. It only see 1 and 0, so this is okay. And the overall accuracy 21% on the whole test set. So every image, so even the digit in that the future digit that I haven't seen yet. Okay, this is the first experience. After the second experience, this is the situation. As you can see, the network has totally forgot. Totally catastrophically 0 in any element, how to deal and how to classify the 0 and the 1. but it only classify with a good result the 2 and the 3s, and the accuracy still stable at maybe 19.80%. So third experience, totally forgot how to deal with the past data. It only deal with the current data here and here. Fourth experience, the same. It classifies only the I think the 6 and the 7. All the past data is completely forgotten, and all the future data, of course, it's not good. Last experience, my network totally forgot how to deal with the past data, and it only works with the 9, with the 8 and the 9. So this is how much the problem is relevant. So this is a very, very simple task, small images, small network, a really, really simple task. If I have all the data, the same network, I think in 2 epochs reach 99 point something percent. But if I want to train it incrementally, as you see, it totally forgot. This is the last experience. All the past knowledge totally forgotten. Okay. Last thing that I want to do is use a continual learning strategy. So for example, here I'm using EWC that I explained you before. EWC want one parameter, which is this lambda. I set to a pretty common value, which is 10 to the 5, so 10,000. Let's see if there is some improvement in using EWC with respect to not using continual learning at all. Hopefully. Let's hope that.
Hi, Gabriele. Sorry.
Hi.
This is João from PySchool. I actually have to go as well.
Oh, okay.
But I see that there is still some people who are here on the call and maybe want to ask you some questions. Okay. So I think I'm going to leave the host of the meeting to Luigi, since he is here. Luigi, give you the big responsibility.
All right, to close the door and the window after everybody.
Exactly, to close the door afterwards. So I'm going to make you a host as well of the call. And I will have to go now, but thank you a lot, Gabriele, for the talk. And I will leave you guys I'll leave you to finalize the talk and to.
Okay.
So for the others also to ask you some questions.
Okay.
All right.
Okay. Yeah. As before, my model currently learning well how to distinguish between 0 and 1. Let's hope that, okay, this is the second experience. So as you can see, the model haven't forgotten how to classify the 0 and 1. Maybe the performance is not good as before. But yeah. With the naive strategy, so not using continual learning at all, we have a 2 column of 0 before. Now we have something here. Let's go ahead. Well, the model, okay, this is not perfect. Maybe you are in an unlucky run, but yeah, there is some knowledge in the model still. Yeah, okay. This is the classical demo effect with nothing works. Okay, maybe we should relaunch this one because nothing worked so well. But yeah, as you can see, it's not so good, but better than using the naive approach. EWC is not the best strategy of all to deal with this problem, especially with the new classes benchmark. So I don't expect this strategy to go very well, but let's hope to have some better results in this run, at least better than the naive. But yeah, basically that's all. That's how you can use the library. As you can see, it's very, very simple. You can do a lot of different things. The library do a lot of different things. A lot of different things are already implemented for you. Okay, I think this run is way better. And as you can see, we are in the second experience here. And yeah, the knowledge about how to classify 0 and 1, it's not forgotten, but it's still here. It's protected by elastic weight consolidation, by EWC. And my model basically can learn new things without forgetting, or not catastrophically forget, how to deal with the past data. Okay, this is basically the Avalanche demo. Okay, if you are still here and if you have some question, I'm here. Maybe write them in the chat or directly open your microphone. Okay, let's see if here there are some questions. Okay. Okay, what is the main difference between continual learning and TL? Okay, if Shadi is still here, what you mean by TL? If you are still here, because
maybe transfer learning, he means.
Okay, transfer learning. Okay, perfect. Well, the main difference is that well, they are very similar, but yeah, basically the same difference is that in transfer learning you basically have some knowledge in one domain, and you want to transfer this knowledge or to another domain, or to another task, or to do something maybe different, and so on, and so on. And you don't really you are not really worried about the loss of knowledge about the old task. So basically you have a model that it's good to solve something, and you want to distill or use the knowledge of this model to learn to do something else. This is typically transfer learning, how it works. In continual learning, it's more like evolving the same model without knowledge transfer. So I always have the same model. I don't want to transfer my knowledge to any other model. I have the same model, and I want to evolve and adapt it to new data and new kinds of situation that can occur in the world. Okay, poi another question. So why regularization is hard in continual learning? Well, basically because it is based on mathematical, it is based on theory. So on paper, it works really, really well. But maybe you know better than me that when the dimensionality of your data, the dimensionality of your parameters, when you have very, very, very large models, when you have a huge amount of parameters, a huge amount of data, the things are not so easy, especially because when you use regularization-based approach, many times you use some approximations, you use some for example, to calculate the Fisher matrix, which is the matrix that I told before that contain the importance of every weight of your model. It's estimated, of course, and if you estimate something, the error propagates. So if I estimate one time, maybe it's acceptable, but if I reiterate this approximation every time I encounter new data, if I encounter new data for, I don't know, 1,000 times, all this approximation error sums up, and at the end I have something that is totally useless. So this is basically why regularization is hard and basically doesn't work well in continual learning, especially when I have high dimensional data and when I have a lot of continual and incremental experiences. Okay, so you can store the data using any cloud service. Yes, you can store it, but beware of the privacy. If you want to deal with private data, you cannot store in Amazon Web Services. Beware of that. You always have to have a working internet connection. Maybe this is not always the case. beware that there are some latency in the data transfer. So, for example, if I want to train my model on the past data, I have to retrieve all the past data from cloud services. This can take some time. If I have a lot of data, maybe the transfer can take more time than the actual learning. And yeah, I can use these cloud services, but beware that there are many problems related to storing data to the cloud, especially for training a model incrementally. You can store it like pre-training algorithm parameters. Yeah, okay. I think MLflow stores the model parameter, store it after training. Yeah, maybe this is related to the previous question about cloud services. Yeah, basically, yeah, you can store your data and your parameters and your model to cloud services, but yeah, beware that you have the cost of retrieving. You always have to have a stable internet connection. What if the cloud is not reachable? What is the cloud company closed? What if the cloud company, I don't know, this is a security breach in the cloud company, and the data is not available anymore, and so on and so forth. So yeah, for the privacy, you cannot use cloud data. There are many different reasons why the cloud is not always the best solution for this for dealing with with catastrophic forgetting. Okay, thank you very much. Okay.
So, just one more question. Just looking to the confusion matrix that is just on the back.
Yeah.
So
here.
It looks like, okay, even it didn't forget what happened before, but there is still a bias toward the last two classes that is so.
Yeah. Of course.
Would you qualify this as some kind of let's call it attention, or is purely a bias? Is more an attention or is bias?
Okay. Yeah. First of all, here I'm used the AWC algorithm mainly. It's maybe because I explained to you in the slides, but it's not the best choice in this case. There are algorithms, there are strategies that work so much better. So and as you say, as you see, different run can have very different results. So the previous run with the AWC, if something goes wrong in the training, this is much better. But yeah, this is a problem of many strategies, and I think it's more a problem. I don't want to call it nor a bias nor an attention problem. It's just that the model is trained only on the last data. So in this case, it's trained on these two classes here. So of course, all the parameters of the model are more pushed to optimize for the current data. So it's pretty normal. For example, in the WC, if you want to do some tests, you can increase. Okay, you can increase this AWC lambda here. For example, more this AWC lambda is high, and more the network is fixed. So in theory, the forget is reduced. More this parameter is high, but it's more difficult to learn new concept. On the other hand, if I put very low value here, learning new concepts, so the bias, we should call it, about the last data that the model saw, it's more pronounced. But so I learn very well how to deal with the new data, but I forgot how to deal with the past. So it's just a question of equilibrium in many situations here. I don't know if I answer your question.
Yeah. No, it's. I understand the point.
Okay. Yeah, you can call it a bias on the past data, because it's the last data that I saw, so I'm more biased to classify all the data in one of the two classes in this case that I see in more recently. So we can call it a bias.
Which, I mean, depending by the application, it can even be a desired quality.
Of course. For example, as I said before, if you want to fine tune the model, so I have a model that correctly classify all the digits between 0 and 7. And I'm only interested in using this model to classify the digit 8 and 9. So only in the last two. I'm not interested in all the other digits. I only want to classify 8 and 9. This is the best strategy is maybe the naive strategy or the fine-tune strategy, where I have all 0 here and it's totally biased on these two classes here, because I'm not interested in the past data. So if my task is it's like it's a fine-tuning task, it's obviously it's a choice to to totally forget and to only focus on the current data. Okay, if there aren't any other questions, I think we can.
I only have the last comment about your operating system, because I see you're using Manjaro and I think you're a hero. I tried it for 6 months, then I rolled back to Ubuntu.
Okay. Well, it's just a it's just a kind of I think habit. I used Manjaro for I think many years, so I'm just I'm just used to this operating system, and for me it's the best. But of course, for other people it can be really a mess, and sometimes it's a mess. But I'm for me
breaking updates. That's what I remember about it.
yeah, of course.
All right. So if there is no further question, Gabriele, we thank you really a lot for your presentation. Just one question. Together with the presentation, could you share also this notebook?
Yeah, of course. I can. I can share the slides and the notebook. Yeah, no problem.
So it would be good. It would be good at least to have some working example that maybe we can put our hand on and
of course,
then change and so on to experiment.
Yeah, use another strategy, change some parameters,
different data set, different so different models. So just because so we it could be useful for at least for some of the projects.
Yeah, of course. Yeah. Okay, so
last question. I see if, from Shadi, if they can use Avalanche with TensorFlow.
Okay. Let me open the chat. Okay. At the moment, no. It's based on PyTorch, so you cannot use it with TensorFlow. But it's a question that many people are currently asking to us. But we are not actually planning to port the library on TensorFlow, because it basically means that we rewrite everything for TensorFlow, because having based on PyTorch, we use all the PyTorch utilities. We code the library in a PyTorch way. So it will be a very huge effort. But maybe in the future, I cannot assure that there will be an Avalanche TensorFlow soon, but maybe in the future, why not?
And then I think also he asked also about the possibility share to contribution for this library.
Yeah, of course. It's an open source project. In the slide there is the website, which is this one here. Okay, it's this is the website of the library. If you go on GitHub here, you can basically download the code. You can contribute. There are some issue open, so maybe there are some issue labeled that feels good issue. So if you want to contribute, maybe start from all the issue labeled as a first good issue, because are maybe the simplest one, the most suitable for newcomers in the development of the library. But of course, you can join us anytime. We are always searching for new contributors. We are 50. And we want to be at least 100, and after that 1,000. So, of course, if you want to contribute, you're more than welcome to this library.
Perfect.
Okay. There are any other questions?
Maybe I can ask something.
Okay.
The last question, hopefully. And we trained this model and on the new data. And I was curious about when is the new data? So how frequently I should train this, and
okay,
how can I determine the time? I mean, is there a clear-cut measure or some threshold?
Okay, well, it depends. It depends on you. Yeah, it basically depends on you. There are scenarios when, for example, you want to train the model as soon as new data arrives. For example, for real-time models, model used to predict, I don't know, some real-time phenomena. As soon as the data arrives, you want to train the model, you want to update the model in order to have a model that it's always updated with the last possible data. Of course, this is not the best case for any scenario, because, for example, if you have a model that I don't know, predict as an example, if some tweets or some post on a social network contains hate speech or not, maybe you don't want to train it every time a person posts something on your social network. Maybe you can want to train it once a month, once a week, once a day. It really depends. So it's really up to you how long you have to wait before triggering a model update. It depends on the nature of the data. It depends how fast the data can drift, how fast can the data can change. If the data change but in a very, very slow manner, it doesn't make sense to update the model every time. On the other hand, if the data can change very often, maybe it makes sense. So yeah, it really depends.
I see. Thank you very much.
No problem. Okay. I think last possibility to ask some question.
Perfect.
Okay, perfect. So thank you very much to have invited me to give this talk. I really enjoyed it. And thank you to all the participants for all the questions. It's really nice every time there are a lot of questions, because it means that people are interested. So thank you very much. And if you have any other question, I leave my email in the slide, so you can contact me. No problem, I will answer. And yeah, have a good rest of the day.
Okay. Thanks a lot, Gabriele.
Thank you.